Right. A concept that's associated with manifolds, particularly in transformation theory, is the notion of connectedness. So we will define various types of connectivity associated with manifolds. The first of these is the straight definition of what we mean by a set being connected. So first of all, a manifold is said to be connected, right? And this definition is written in terms of a negative. If it cannot be written as if it cannot be written as a disjoint set, a disjoint union of open set, cannot be, and this is the emphasis, cannot be written as a disjoint union of open sets. So this is a disjoint union of open sets. I.e., it cannot be, and this is the important thing, it cannot be as M, if that is your manifold, a union of, say, some open sets where the open sets are disjoint. So if it can be written as a disjoint union of open sets, or it's a union, then this would be satisfied. It's clear that this notion of connectedness is, it would allow, if the set is connected, you'd be able to go from one point on this manifold to another point. Whereas if you have this scenario where it can be written as a union of these open sets that are disjoint, then you might be able to block off these points. So you have a point here and then another point there, and you might not be able to get from this point to that point because of these disconnected sets surrounding these points. So connectivity may not be allowed in this sense. The second notion of connectedness is what we call path connected. So a manifold is path connected, and this one is almost obvious in its definition. It is path connected if between any 2 points on the manifold, and remember, points on a manifold are equivalent to vectors, or at least can be embedded in vectors of some dimension. If between any 2 points in the manifold, there exists a path connecting the two. Of course, the path has to be on the manifold. There exists a path connecting the 2 points. So this one is pretty obvious what that is. And the next one is quite interesting, and that is the notion of simply connected. So M, a manifold, is simply connected, right? If every closed path in the manifold can be reduced on the manifold, successfully reduced. That means without breaking the closed path, can be reduced to a point. and this one is also an important notion of connectedness. A classic example of this is that if you take the manifold R2, so this is the whole of R2, right? But excluding the origin. So this is certainly a manifold. And if I were to draw a path, like this path easily would successfully reduce to a point. But if you take this path, for example, right? That's a path in the set, but it cannot be reduced to a point unless you break that path, and that's not allowed. So this there is not simply connected. And if you take the equivalent one in R3, right? So if you take this set, now this one is in R3. If you take any path, even if it's supposedly going around the origin in R3, so if you were to take any path there, you'll be able to reduce it to a point. So this, incidentally, I'd like to remove the origin in this one too. So let's exclude the origin. So this is the set R3 minus the origin in R3. This one is simply connected. So this one is simply connected. So these are the notions that will come up, or at least should come up when we talking eventually on the aspect of transformation. In transformation theory, as the word suggests, we are transforming points of a manifold. So from one point you're transforming via a mapping to another point also on the manifold. So this is where this notion will creep up. Right, so we're going to stop this notion of manifold now. We're going to speak of sets in the algebraic sense. So the concept we're going to refer to is the notion of groups. And you have probably come across this in any basic course in algebra, and the notion of groups is an important notion, algebraic property in groups, in algebra. So unlike in manifolds, recall that the definition of manifolds said that a set is a manifold if it can be embedded in Rm for some m. No notion of operations, that means addition, multiplication, or whatever it is, no operations between the elements of the manifold. Here, to define a set being a group, we have to have an operation. So a set is a group if there exists an operation. So instead of saying that, so let's say a set with an operation, and I'm going to give the operation a general notation. Let's call that operation that. So this could represent addition, multiplication, multiplication of matrices, depending on the context of the set and the definition. So a set with some operation, right, is a group. Now let's give the set a name. A set X, capital X, with an I think a better notation would be G, wouldn't it? A set G, capital G, with an operation is a group if it is closed. If it is closed, that means if you, with respect to this operation, of course, that if you take two elements x and y from G, then x dot y should be in the set G2. So we're assuming closure, obviously, and some other properties that needs to be satisfied. One is that for all little g, little h in the group, I was going to put in a third one, gh, say k, in the group, we have the property of associativity. In other words, that if you were to take first of all h and operate with k, that should belong into the group, in the group because of closure. And if you operate that with g, then you want this to be the same as doing, say, g with h first and that with k eventually. You want these two things to be equal. So remember, the bracket means you want to do that first. So the order in which you do this operation between g, h and k doesn't matter. Right. The second property, and it's an important property of groups, is that there should be an identity element, right? So that means there exists E in the group such that if you were to operate E with any element in the group, you get back that element. It's like, as far as multiplication is concerned, if you take the number 1 and multiply it to anything, you get back anything. Of course, if your operation was addition, then your identity would be 0, because 0 plus anything will give you anything. This E is, of course, called the identity element. Now, once the identity is defined, then for every element in the set, we define, or there exists an inverse of that element. So for all g in G, there exists a corresponding element. Now here, this next thing is merely a notation. You can call it G star, you can call it G to the minus 1, you can call it whatever you like, but it's unique to G. So for all G in G, there exists, say, G to the minus 1. If you're not comfortable calling this minus 1, perhaps I should call it G star. There exists a G star also in G, unique to G, such that when you compose or you operate G with this G star, you get the identity. So G star is merely a notation. Now we have, of course, some obvious standard examples of groups. So let me just mention one of these, or some of these examples. One, if you were to take the real line with ordinary addition as your operation, so that's merely a notation. Perhaps I should change this notation. Let's write it as subscript as opposed to superscript. So if you say this is your real line, right, with operation, that means your dot with operation addition. So this is your ordinary notion of addition. Once you define the set of real numbers with addition as your operation, and obviously if you add any two numbers, they belong to the real line, so it's closed. The order in which you multiply any three, add any three numbers doesn't matter. But having defined this addition as the operation, then the identity element will be 0, because E plus, that's your operation, plus anything in the real set will be equal to 0 plus being the operation, that, and 0 plus anything is anything. and if any element is in the set, because the identity is 0, the corresponding inverse would be the negative of that element. So I should say for all G in the real 9, your G star will be in fact equal to minus G, because if you take G and if you add it to G star, then this is equal to G plus, of course in this case your inverse element to G is minus G, and this is clearly equal to 0, which is the identity of the set. Once you take your real line, this time let's exclude 0, right? And this time let's say it's the real set with ordinary multiplication as your operation. So now the operation is in fact ordinary multiplication. So with this being the operation, ordinary multiplication that is, then of course if you multiply any 3 numbers in any order, nothing changes. If you multiply any 2 numbers, they belong to the set, so you've got closure and associativity. But now of course the identity changes. So here then your identity will be equal to the number 1, and the reason of that is clearly if you take any G in this set of real lines with multiplication as your operation, then E, your identity multiplied by G, that's your identity operator, the element, that is going to be equal to your number 1 times your element, and that's going to give you back G, clearly, right? And the inverse of any G will be your usual 1 over G, and G star, your inverse of any G is your normal 1 over G, right? Because if you were to take G and operate with its inverse, the inverse is defined as your usual 1 over G. If you multiply G with 1 over G, you get 1, which happens to be the identity of the set. Right, let's look at some basic examples. Let's suppose we look at the general linear group of n by n matrices with real entries that are invertible. So these are your n by n matrices that are invertible. And these of course have real entries that R indicates real entries. This is of course a group. If you define multiplication or the operation, so here you would define of course your operator to be your ordinary matrix multiplication. Now once you've defined this as your operator, then your identity element E is of course equal to your identity matrix of dimension n, and the inverse of every element of the set, the inverse of every matrix, is just your usual inverse of the matrix. Okay, so this is a group. A subgroup of this is your special linear group. That is, again, these are n by n matrices with real entries, invertible, but here we put in the extra condition on these matrices that they have determinant equal to 1. So matrices with determinant 1. 1. If you multiply any two matrices with determinant 1, you get a matrix with determinant 1, etc., etc. It's closed. The operator, the identity will be the identity matrix, and the inverse of any matrix is a usual matrix inverse. These are your some standard examples that arise. There are some special cases, of course, of this. You've got maybe a sub-example of this is your special linear group of 2 by 2 matrices. So this is just a special case of number 4 where you have 2 by 2 matrices. Then, of course, you've got the SO2R. This will be the subset of number 5, in which you've got 2 by 2 matrices, invertible, they form a group certainly, of determinant 1, but we have the special additional property that given any matrix, the inverse of the matrix is the transpose of that matrix. So this too, number 6, is also a group. So these are special cases or special examples of sets that are groups.